Good morning, everyone. It's sunny and beautiful in San Francisco here today, but good morning to everyone everywhere else in the world, and good afternoon, good evening as well if you're watching in different time zones. My name is David Skenazy, and today I'll be talking about Quic. So I am one of the tech leads for Quic and Chrome networking here at Google. But I want to particularly thank Jana Iyengar, who helped write most of the content in these slides today. So let's jump right in. Everything that or almost everything that I'm going to cover today was published at SIGCOMM, one of the leading networking conferences in 2017. So if you want to drill down into more detail and get access to the actual numbers, whereas today I'll just do a high-level overview, feel free to dig down into this article. This paper, sorry. All right, so what is Quic and why do we care? What is interesting and why are we here to talk about it? So Quic was an effort started at Google quite a few years ago to have a better protocol for HTTPS traffic. So in particular, aimed at the web, but it's evolved since to encompass other use cases. So it was deployed initially between Chrome and Google services and significantly improved quality of experience for our users, such as, for example, the YouTube videos would not do the spinny rebuffering quite as much, and the latency of Google search results was also improved. And now it's representing an ever-growing amount of Google's traffic, and it's over a third, and we expect it to increase in the near future as well. And the part of the life of this protocol involved first developing it inside Google, but then making it open so the entire industry could benefit. And we were working with the IETF, so that's the Internet Engineering Task Force, the standards body that regulates protocols on the internet, and we're working with them to make Quic an IETF standard. So in terms of our deployment, you can see these are numbers that are a little bit dated, but you can see how it improved quite a bit. Apart from that one dip in early 2016, where we realized that we had a security vulnerability at the time. And so we immediately completely cut off traffic until that was completely diagnosed and fixed. But apart from that, it's been very much a steady increase, and it's growing even more today. So Quic didn't happen in a vacuum. It's really sitting on the shoulders of giants. So if you are watching live, the next session on track A here will be a talk by Vince Cerf, father of the internet, of some of this history there. So I highly recommend watching that. If you're watching the recording at a later date, I might even suggest watching that talk first. So let's have a quick overview of how packet switch networks and the internet works. One of the founding principles of the internet compared to other competing systems at the time was the end-to-end principle. The idea that you put the complexity on the edges of the network and you have something simple and cheaper in the middle. And what that means in terms of a networking protocol stack is that both ends of your communication, so let's say your client device has a web browser on one end and the website you're talking to on the other, have to understand TCP, but everything in the middle, all they have to speak is IP. And so you end up kind of creating a layer of abstraction where it feels like TCP gives you a connected byte stream between both endpoints, and you kind of forget about all these IP nodes in the middle. And then on top of TCP, you can add HTTP. And so that's our application layer protocol and pretty much the underpinning for all web traffic. One of the downsides with this model is it was developed in an era where computer security was not as front of everyone's mind as it is today. And so just anyone observing traffic somewhere on the middle could see what website you're talking to and exactly what you were telling them. So even your passwords, your credit card numbers. So that's really not great. So what happened? Initially, SSL, which became TLS, was developed as a way to encrypt and authenticate and prevent tampering of the application layer data. So now what you communicate to and from a website is no longer visible to this random observer, and you can safely type in your passwords, your credit card numbers, knowing that you are giving it to the server and not to just anyone who's listening along the way. So taking a step there in the history of HTTP, so the original version, the first standardized as 1.0 version of HTTP, but also the previous ones, required a separate TCP connection for every HTTP request and response. And as papers dating back to at least 1995 show, there is clearly that was a performance issue, because TCP takes a while to ramp up to use the entire congestion window and to use all of the throughput available on your link. And if you're doing a bunch of requests, everyone kind of needs to learn for itself because they're independent, and that has a cost. So there was an effort back then called HTTP NG. Ever since Star Trek, a lot of IETF things are called NG, but that's just how it is. But the idea was to try to improve some of these problems. And in particular, okay, how can we, a web page is no longer a single page. We load the HTML, but there's also images, JavaScript, CSS, a lot more sub-resources now. And if you have to load all of them separately, it could be a problem. So an effort was started to try to improve this performance of this very common web use workload. And so, adding to these problems that were mentioned, you also, when you have separate connections, you can't make as good scheduling decisions, because from the client, you know that those two connections are tied, but from the server, you don't necessarily know that, sorry, that they come from the same client. So kind of one of the fundamental things was, okay, how about we multiplex multiple of these HTTP requests onto the same underlying TCP connection? And so this became, so a concrete proposal to do this was Speedy. So Speedy was developed in the early 2010s by Google. So similarly, it was a partnership between Chrome and Google Services teams, and the idea was, all right, let's implement this new protocol in Chromium, let's implement it on servers and see if we can actually move the web forward, if we can make web pages load faster for users. And the answer was yes. So the main features that Speedy had were streams and multiplexing. So that the idea being that instead of every HTTP request response mapping to a TCP connection, they map to a stream, which is a conceptual abstraction that looks very much like a TCP connection, but that is kind of inside another TCP connection. So for that to work, you need a mechanism to multiplex between multiple streams. It also allowed providing flow control, meaning if you have a bunch of resources, TCP already at the TCP level allows the receiver to say, oh, hold on, don't send me too much at once. I'm not going to buffer infinite amounts of data that I can't consume just yet. So Speedy allowed you on the stream level to say, hey, hold on, like this giant file download, let's back off on this one. However, this like JavaScript, let's get that going really fast. And similarly, priorities allow you to tell like your peer which of the streams you want to get sent first. Because for example, let's say as a web browser, if you're loading two images and one is on screen and one is like off screen, the user hasn't scrolled there yet, you want the on-screen one to be delivered first because that's what the user will notice. Whereas the other one, if it arrives later, it won't really matter until the user scrolls there. So Speedy had all of these properties. And so it was a great success. It really improved performance or properties. So the team brought it to the IETF and eventually it became HTTP2. So that was standardized in 2015 and is currently the stable version of HTTP used pretty widely around the internet. And if we go back to our stack model, HTTP2 lives over TLS again, you want all that to be encrypted, and you want the server you're talking to be authenticated. And so HTTP2 gives you all of that. But now that the team kind of improved HTTP, the question is, well, is there anything that could be done at the transport layer? Can TCP be improved? Like UDP and TCP date back quite a while, and there have been efforts to work on this. So like TTCP was an idea there. Another one was TCP session. There have been efforts over the years to improve TCP and add some of these features that we're talking about at the TCP layer. Some say that like it would have been great for TCP to have all those features when it was first created, but at the time, like TCP was meant kind of as a replacement for a serial port, which was just like a reliable bidirectional byte stream. So that was the main feature that they wanted. All of these new features, we really kind of sort of realized that they were really important later. So SCTP was a take on adding quite a few features to TCP. It had some success in like telephone networks, but it was never really deployed as a replacement for TCP on the internet. Part of that has to do with middle boxes, which we'll discuss a little bit later. And then another TCP improvement that was really geared on performance was this idea that, so in TCP, you have to do a three-way handshake before you can start sending data. And the main motivation for that is security. It allows the server to verify that the client actually is in possession of this IP address and isn't just sending packets with bogus source addresses to try to overload the server. But in some cases, if it's a client that you trust, maybe you don't need that. So the idea with TCP Fast Open is like the first time you do a full TCP three-way handshake, and the server gives you a cryptographic token that you can then use on a subsequent connection to come back with this and say, no, it's me from last time. Trust me, we can skip the handshake and go faster. And that allows you to save one round trip, which makes a huge difference on the internet today. We're talking at least 100 milliseconds for most users, and sometimes way more if folks are in markets that are further away from data centers. And finally, MPTCP was another effort to allow TCP to survive to path changes. So meaning, like TCP is very tied to the IP addresses that it uses. So if your cell phone is connected over Wi-Fi and you switch over to cellular, that's going to have a different local IP provided to you by the cellular network, and TCP will break. MPTCP allows to just seamlessly transition that connection without the application level abstraction breaking. It also, even in some circumstances, allow you to send on multiple paths to like increase your throughput. So I mentioned middle boxes earlier. So what are they? So when we were talking earlier about the model of the internet and this diagram and the end-to-end principle, there was this idea that the middle of the network is very simple and the complexity is on the edges. A middle box is a box that kind of breaks that, and that is in the middle of the network and tries to be smart. And so in some cases, like they make sense. So take most networks today on IPv4 have a NAT because there isn't enough IPv4 space. So your internet provider will hand you one address, and your like any off-the-shelf Wi-Fi access point and router that you buy will have a NAT gateway inside of it that allows giving private addresses inside the network, and then as the packets fly by, it rewrites them. Other examples of middle boxes are firewalls. So like a security device that looks inside the parts of the packet to decide, oh, this shouldn't go through here or not. They're application load balancers. So often on the web, many servers deploy those to like, when you talk to a server as a client, you're not actually talking to the backend, you're talking to a front end, and then load balances between multiple backends. And then PEP, so performance enhancing proxies, are devices that try to improve performance in the network. Some of them, for example, will terminate your TCP connection from the client to them and then create a separate one from them to the server in an effort to improve performance. Unfortunately, that doesn't work really well today. So the main problem with middle boxes is they're meddling into protocols that they didn't have a reason to be in, and so like this orange box here really wasn't designed like TLS, TCP, like these end-to-end protocols weren't designed for this meddling. And so take, for example, if you use vanilla TCP, the middle box that's trying to accelerate things will say, oh, sure, I know TCP, I'll implement TCP. But what happens when you try to improve TCP? So when TCP Fast Open came out, there were middle boxes out there that said, wait a minute, this SYN has, which is the first packet in TCP connection, this SYN has data on it. That's not legal in TCP. This must be an evil client. Let's blacklist and block their IP for like 10 minutes, making like that all of a sudden your web browser becomes completely unusable because this box that was trying to be clever and helpful actually misunderstood what you were trying to do. And there have been many instances of this. Similarly, SCTP was never able to get deployed on the internet because NATs understand TCP and UDP and pretty much nothing else. So going back to Quic, so if we look at our HTTPS stack, you run HTTP over TLS or TCP over IP. And what does Quic look like? So this is the, so one important note. So as we mentioned earlier, Quic was a protocol that was initially developed by Google, which was then handed over to the IETF, which like evolved it over time. And so there are kind of two protocols now. One is like called Google Quic, or G-Quic for short, was the original one from Google. And IETF Quic is the one that is going to become a standard. And Google is very committed to evolving Google Quic to become IETF Quic. And we recently shipped IETF Quic in Chromium to like all users last month. So that was a huge milestone for our team that we were really happy about. But look, coming back to here, so this is in G-Quic, in the old Quic model, you can see that it doesn't live on top of TCP, it lives on top of UDP. And I just want to be like very clear about something because it's a common misconception. This isn't why it's faster. Like UDP isn't faster than TCP. Like there are different protocols that give you different properties. Like if you want something to be sent reliably, let's say your web browser is trying to download an image, you're going to need the full image. You don't want like bits and pieces. And so you need an abstraction that will send it to you reliably, even if the network drops some packets, because that's one of the properties of the internet. Sometimes things get lost. And so TCP will take care of that. UDP won't. UDP is just here's a packet. If it gets there, it does. If it doesn't, sorry, good luck. So this is why here the box is a lot smaller. UDP pretty much gives you no properties over IP apart from port numbers and a very small checksum. And then Quic has to do all the heavy lifting. So Quic has to implement the congestion control of TCP to make sure it doesn't overload the network, the flow control of TCP to make sure it doesn't overload the peer, the loss retransmission, or loss recovery. So if a packet gets lost in the network, that data eventually gets there. So eventually, your file download does complete. Also TLS, so Quic needs a security model, it needs encryption, it needs to verify the TLS certificate of the server and things like that. And then inside that, there's also HTTP. So it becomes a bit clear with the IETF model, which ended up with somewhat of a cleaner abstraction, where a lot of the work happens in Quic. So take, for example, what we had looked at in HTTP2, like the multiplexing, the streams, the flow control, all of that moved from the HTTP layer to the Quic layer because that's a useful property of a transport and not necessarily restricted to HTTP. And then TLS is off on the side because Quic uses TLS for its key exchange properties, for its certificate verification, and for generated all the keys it needs, but it doesn't actually work on top of the TLS protocol. So that's why it's kind of on the side with arrows there. And then HTTP3 gives you all the mappings of the HTTP semantics on top of this new transport. So the stack ends up looking like this, where you have HTTP3 over Quic over UDP and IP. Let's talk about some of the design goals along the way. So one of the important properties of Quic was that it wanted to kind of change the landscape in networking. And one of the problems in networking is that it's really hard to evolve things when you have to modify many devices. And so let's say, modifying IP requires changing every router on the internet, and IPv6 is still taking a very long time to deploy because of that. But if we say, okay, let's really have an end-to-end principle, and we only need to modify the client and the server, and even more than that, maybe we only need to modify the application instead of the kernel, that gives us a lot more flexibility. So especially in our shoes, we can modify Chrome, and Chrome has a very good update strategy every 6 weeks. And similarly, we can update Google servers, and those update pretty frequently. And so let's build a transport in user space so we can iterate very quickly inside Chrome instead of having to rely on the operating system updates to update TCP inside the kernel, which in some cases can take a very long time. Oh, and another part is because of these issues with middle boxes, let's encrypt everything so that it becomes harder to actually mess with it. So a quick aside for why this is important. So the first byte of the Google Quic packet was a flags byte. So 8 bits that were all just different flags. And they were sent in the clear, and just because of what had happened, the first packet would always have value 7. So 3 bits flipped and the other one's 0. And that's just how it was. But that doesn't mean that it would always be like that. It just meant that that's just how it is. Some middle box vendor looked at Wireshark. Well, actually, backing up, we actually flipped one of those bits. We said, oh, this one's free. We need it to communicate some information to the server. Let's use this other bit. And then the packet had something different. And we started getting reports from vendors that, wait, our enterprise users can't access Google at all using Chrome, which is really bad. So we investigated. It turns out some firewall vendor had decided that they didn't read any of the specifications. They just looked at Wireshark and said, oh, the first byte is always 7. So that's a property of Quic. The first byte is always 7. Let's put this in our code. If the first byte of the payload is 7, it's Quic. Problem there is they let the first packet through in both directions, meaning that Quic connected fine and told the application or the higher stacks of the browser, hey, we're connected, everything's fine. We don't need to fall back to TCP. Quic is working. Let's send all the traffic over Quic. But then all of the next packets were dropped by the firewall. And so it meant that none of the HTTP requests could get through and the users couldn't browse any Google properties. So that was really bad. So the important lesson there is, if you want to retain this end-to-end property, this idea that both sides can modify things without having to modify everything along the way, you need to defend the end-to-end principle, and the best defense is encryption. Because if you encrypt these bits between the client with keys that only the client and the server have, then there is no way a middle box can go and either modify them or look at them and react differently to them. So it prevents them from actually drilling into the protocol in such a way that prevents you from modifying it later. And so that's really important. And hence, that is why in Quic, pretty much everything is encrypted and authenticated to prevent attackers from modifying things. And then other really important design goals of Quic were performance. So let's make connecting as fast as possible. So they did something that is referred to as zero RTT, as in normally you say, okay, so our RTT means round trip time. So how many back and forths do I need to do with my server before I can actually send a request? And so in traditional TCP with TLS, you need to first send your TCP SYN, get your handshake back, then your TLS client hello, and get the TLS server hello. With older versions of TLS, that was in yet another one, so we needed 2 or 3 round trips. With Quic, we call it 0 round trips, because if you've had a prior connection to that server and it's given you some cookies and cryptographic keys, you can use those to send your first request immediately. You don't need to do that handshake. You will do the handshake, but you send the request kind of all alongside that handshake. And that makes a huge difference for users. And the more, like, the higher their latency, the more of a win this is. And additionally, what we talked about, bringing these concepts of streams and multiplexing that were in HTTP2 down to the transport layer, where it made more sense to have them there. And then additionally, all right, since we're changing or building something that is at the same level as TCP, can we learn from TCP and make improvements? Because TCP has served us incredibly well. Like, the internet has worked great. It has scaled from way before dial-up modems to gigabit speeds, no problem. But that doesn't mean we can't improve it. And one of the very hard problems in TCP and network transport protocols in general is when should I resend something? Let's say I've sent a packet. When should I assume that it's been lost and resend it? And the general best way to do that is to have very accurate measurements about the round trip time and say, okay, I sent it there. I would have expected an acknowledgement by this time. I'm going to wait a bit longer because of jitter. But if by this point I haven't received it, then it probably was lost. So I'm going to send it again. In TCP, that's pretty tricky to do, because let's say if you send a retransmission, it's going to have the same sequence number as the first time you sent it. And so on the receiver, or even in the other direction, when you're receiving an acknowledgement, you don't necessarily know if this is in response to your first packet or the second one. And that uncertainty makes implementing TCP a lot harder. It also means that you have to make heuristics to answer these questions, and heuristics can get things wrong. And similarly, if it's pretty common to do techniques like stretch hack, where in TCP, you don't acknowledge a packet immediately, you kind of wait for more to come in. But on the other side, if your peer has waited a while before responding, you don't know if that delay was, oh, they just waited a while, or no, the network is getting congested, some queue in a router is growing, and I should back off. And so Quic solves all these problems by having a packet number that is separate from the stream sequence numbers, and that is always incremented. So if I retransmit something, it'll be a separate packet with its new packet number, and it'll have its own acknowledgement. So I will know exactly which one it was. And the acknowledgements also carry some timing information about how long between when this device received the packet and it sent the acknowledgement for it. And so that way, on the other side, you can deduct that to get a very good picture of what the round trip time is. And at the end of the day, and we've noticed this very clearly in like overall aggregated performance numbers, this makes a difference in terms of like user visible metrics, like page load times and things like that. And another important feature is connection migration. So like we mentioned earlier, in TCP, if your IP changes or like your let's say interface changes, everything falls over. Quic is really resilient to that. Every packet carries a connection identifier, and that allows you to, if the packet comes from another IP, you can still route it to the right place based on this connection identifier. And that makes huge wins on mobile devices where, let's say you're walking out of your house and you're doing navigation instructions to get somewhere. You can start off that connection over Wi-Fi. It'll seamlessly keep going over cellular. And that, again, made huge performance wins. And similarly, NATs have, they're stateful. They need to keep track of which of port mappings, which port maps to which internal addresses. And sometimes either if they crash or if they run out of memory, they'll remove those mappings. And like your TCP connections will fail if that happens. Quic connection migration allows you to seamlessly handle this, because if your NAT remaps and you have a different port, Quic will be able to cover thanks to this connection identifier. So looking pretty briefly at some performance numbers, you can see how, based on some networks, Quic, pretty much the slower your network is, the more improvement Quic gets you, because at the end of the day, like Quic can save like entire round trips, and the longer that is, the more of a win. And similar, like if your network doesn't work very well, you're going to be like on the edge of congestion control problems the entire time. And so improving how we handle congestion control, again, very noticeable user weights. So what's it looking like right now? So the work at the IETF has happened for like the past 4 years. And just last month, the documents entered what is called IETF last call, which means that they're almost done. We're like adding some finishing touches. It's like going through further review by anyone in the community. And by the way, if anyone is interested, you're welcome to join like the mailing list at IETF and comment on this. Like these are the kind of the last times we can make these comments in a way that'll change the protocol, because once it's published, it's final. And so we're expecting it to be published next year in 2021. There's been a lot of discussion because all this encryption to ensure that the protocol can evolve has made some network operators' lives harder, because they used to look at this TCP information to, for example, look at the health of their network, and that information is no longer available. That's unfortunately one of the trade-offs we had to make. And another properties that the IETF is really focusing on is, so we already talked about encryption. Grease is a great idea where it doesn't matter if you design your protocol to be extensible and say, okay, insert extensions here, if the other side, when you add an extension, like crashes, for example. And so the concept of grease is you pick a small set of joints that you want to use for extension, and every so often you send like a random value with an extension that does nothing, and just to make sure that the server properly ignores extensions that it doesn't know. And the idea being, if you do that from the start, and even as part of protocol design, if someone writes a server that like falls over on unknown extensions, they will like from the get-go crash all the time. And so those engineers will fix that bug before they ship. Whereas in the past, if we didn't do this, you would end up with someone shipping something like this, and then years later, when you want to use your extension point, you realize you can't, because that server is like widespread and you can't easily update all the instances. So a lot of lessons learned here over the last many decades have gone into Quic. So now it's really no longer a Google project. So Google has an implementation of both Google Quic and IETF Quic, and like it's open source in Chromium, but many other players across the industry, so both like clients like Apple and servers like Cloudflare, Fastly, and many others are working on their own Quic implementations, and they interoperate well, which shows that like the standard is pretty mature. And this also means that like we're expecting as they all deploy this to production, these implementations to production, we're really expecting like global Quic usage to increase dramatically. Let's see, how much time do we have left? Yeah, we're running a bit low on time, so I'm gonna just quickly breeze through. So pretty much for older things, you could use Wireshark for everything, but as in like modern days, with everything being encrypted, plus like a lot of information not being sent on the wire, like tooling on the endpoints is a much better option. And so Chrome has our own netlog format. There are other formats out there, but the idea is that you ask the endpoints to log some information, and then you can use those to visualize them. So Quick Trace is an example from Victor Vassiliev at Google that emulates TCP trace, but in a way that works for Quic. And QViz is a project by Robin Marks and others that does many different visualizations of what's going on in a Quic connection. And it's been incredibly helpful to help us diagnose issues. So just to quickly go through like what the packets actually look like, you At the start of a connection, you use this long header that allows you to negotiate some parameters, like all the connection identifiers and the version that's in use. But after that, everything is what we call short headers. And what's in the red circles here, or rectangles, is encrypted. And so if you look at the short header packet, there's nothing that middle boxes can mess with at this point, because like everything is encrypted, or almost everything is encrypted, and the last few bits that aren't are authenticated and integrity protected. So it prevents them from changing them, even though they can see them. But take like the connection ID, even if they can see it, it doesn't really matter. It's just a random opaque bag of bits, and so they can't act on it. And so this is a really important, great property that will allow us to keep evolving Quic over time to like take, you know, bleeding edge research in networking protocols and bring it to users around the world. So yeah, this is like a quick view of how you build Quic packets. I'm going to skim through this because we're out of time. But pretty much the idea is that now you can kind of, inside a Quic packet, send data from multiple streams and send an ACK in there, and that allows you to really do this multiplexing in a way that's very clean and like very efficient. And yeah, we can skip this. And now we have time for questions. So we're using Slido for questions today. Yes, please feel free to add your questions in there. All right, I'll stay here for a little bit in case any questions come in, but otherwise that'll be a wrap. All right, then I guess that's it for me. Thanks everyone for watching.